Okay, so I'm going to be trying to give you a little bit of a feel for some of the ways that artificial intelligence is being used today in space exploration. And I'm going to tie this in with my favorite topic, which is how can we discover life beyond this Earth, within our solar system and actually beyond our solar system. So a lot of people don't know this, but artificial intelligence is used in almost all aspects of space exploration. And I'm going to start out by making a disclaimer here. I'm going to try and give you a whirlwind tour of some of the many ways that AI is being used in space, but this is not, by all means, not intended to be an exhaustive list. So there's lots of great work that I'm not going to be covering going on all over the world, the European Space Agency, other NASA centers, Space Telescope Science Institute, and so on. I'm just trying to give you a flavor for what's happening in space. So one of the big things that happened in artificial intelligence space is in 2003. In 2003, we got the right to actually upload some software to a spacecraft called Earth Observing 1. So there are some things about Earth Observing 1 that are very mundane. So it's flying at 7.5 kilometers a second, it's a 1-ton spacecraft, and it's 700 kilometers overhead, yet it can pick out different crops and things beneath us. But the unusual thing about this is it had AI software. And what did that AI software allow us to do? It allowed us to acquire different images, analyze them on board, and make decisions on its own and tell us later about it. And some of the things that it would do is it would take these images, it would analyze them and say, well, that's a very cloudy scene, I know you don't want that, let's delete it and let's try and take another scene. We also had the ability to detect different kinds of events. So this particular video is showing we're overflying the Mount Etna volcano in Sicily, and we actually can extract the thermal signature of the eruption, and we can decide, wow, there's an eruption going on at Mount Etna, maybe on my next overflight I should take more images. Or maybe I should send an urgent message down, not the whole image data set, and tell people that this volcano is erupting. Or what's even better than that? What's even better than AI on one spacecraft? It's AI on a whole set of spacecraft talking together. Maybe they're still not quite communicating with humans like Rao wants, but at least the spacecraft are talking to each other and getting along. And what we have here is we link together different spacecraft, particularly in particular metaphors, where we have one spacecraft that can see a lot, but not very precisely. This is the MODIS instrument on the Terra and Aqua spacecraft, and it can automatically detect forest fires, detect volcanic eruptions, detect flooding, and tell another spacecraft that can't see as broadly, like EO1. MODIS can see 2,700 kilometers wide, but only at 1 kilometer resolution, or 250 meters per pixel. EO1 can see at 30 meters per pixel, but only 7 kilometers wide. So they talk together, and you can automatically task one spacecraft from the other. And this is a very much more effective way of tracking everything that's going on the Earth. We applied this to flooding, and we were able to double our ability to get high-resolution imagery of flooding in Thailand. And this was very important in the flooding campaigns of 2010, 2011, 2012, where hundreds of thousands of people were driven out of their homes, billions of dollars of damage happened, and these products are used by the NGOs and actually the government, our collaborators, the Hydroagroinformatics Institute, to actually mitigate the flooding and control the floodgates. We also use this to monitor volcanoes worldwide. We're so effective that if you take our accuracy at our triggered observations, over 35% of them captured active volcanism. The other standard measurement techniques are over 100 times worse. They have a hit rate of somewhere between 0.03 and 0.3%. So these are ways that we can monitor the world around us, and that's one of the goals of NASA and other space agencies, to understand what's going on in the Earth around us for the betterment of humanity. Whoops. So how do we do this? What kinds of AI do we use? Well, one of the things that we do is we do various kinds of machine learning, and I'm going to give you lots of examples of what Rao was talking about with data-intensive AI. So this is actually Bayesian classification in trying to detect clouds. And so this is the snow, this is the land, this is the clouds, and we can determine these different thresholds in a multi-dimensional space, and we're looking at data that humans can't interpret very well. So as humans, in our visible data, we look at things roughly in 3 different kinds of color. You can think of this as the red, green, and blue. we can build instruments that can look at different spectra. These are all different wavelengths in the electromagnetic spectra, and in effect, they're looking with hundreds or potentially even thousands of different of these spectra. So they can see things that we can't see with the human eye. But people can't figure out how to interpret this 100-dimensional space very well. So mathematically, the software can figure out these decision boundaries and distinguish between things that are very hard to distinguish, but in this multi-dimensional space, it's not so hard. So snow and clouds, or ice and clouds, or water and clouds are actually very hard to distinguish in satellite imagery because they're all water in different phases. In fact, the clouds can actually be ice clouds or water vapor clouds as well. So this is exactly the kind of thing that we want to use to detect the clouds in the images, and we also use this to store our data more effectively. Some of the instruments, they don't like clouds, so they recognize the clouds conservatively here. We can actually recognize them more aggressively or conservatively, and they compress that data very much so that we can bring down more of the information that we want to bring down. Even as far back as 2005, we were applying support vector machine learning. That was all the rage in the 2000s, and using it for this kind of problem. More recently, we have a system called TextureCam, which implements random decision forests, random decision forest machine learning techniques, and actually implements them in FPGAs, directly in hardware. And we like this because we have not very good computers on board our spacecraft, and so we can process larger amounts of data with this other kind of hardware. This is again showing cloud classification, and then some of you already know there's very clever ways of training all these different decision trees, and then they vote, and then you can get a better classifier because it's doing some kind of ensemble classification. So sort of like the wisdom of the crowds. Oops. Uh-oh. And the most sophisticated onboard smarts and image processing that we fly is actually something that's called onboard spectral analysis, or hyperspectral unmixing. So I said before that we have these instruments that can see things in this 100-dimensional space. And so it turns out when you have all these different information on board, you can actually determine what kinds of minerals are on the ground, even though they're very faint. They may only be 2 or 3% if they have these distinct spectral signatures. So we can actually, this is actually a scene from Cooperite, Nevada, where we can actually determine what kind of minerals are on the surface of the ground from 700 kilometers away and say, this is alunite, this is muscovite, this is calcite. We demonstrated that we can do this onboard analysis that's just as accurate as the manual ground analysis. So this has huge applications in determining what kind of plants are there. Some of the humanitarian applications are you can actually detect what's called the green up and predict the onset of higher incidences of malaria, dengue fever, and rift fever. And so these are ways in which these kinds of very unique applications of AI can help humanity. And it's not just in supervised learning. There are ways that we can use unsupervised machine learning. By doing outlier analysis, we can pull out things that are unusual in scenes. This is actually a rural scene in Thailand. It's got a river here, it's got different crops, it's got a road, and immediately everybody, normally, the humans are all drawn to this area. Why is that? Because it's very different from the rest. So it turns out those are a bunch of buildings, and the rest of this is natural. And so if you look at the colors, if you look at even this 100-dimensional spectral space, you get exactly that kind of information. And so this technique is very powerful. If you have a scene that's all green and you have a blue spot, it's going to pull that out. If it's all blue and you have a green spot, it's going to pull that out. And in fact, if you have a scene that's all smooth and there's a rough spot, it'll pull that out. That's kind of what we want to do. And this is very important when you're exploring an alien terrain, someplace where you've never been before. This is an experiment where we use clustering and metric learning to figure out how we would send back images of an alien planet that we went to. Now, of course, you can all look at this and say, well, this is actually from a summer intern who flew across the United States and took hundreds of pictures outside the window of the airplane. But imagine that we're exploring an alien world. So two famous explorers, Lewis and Clark, they went all the way from the central United States or central North America to the Pacific Northwest. And they saw Great Plains, and they saw mountains, and they saw waterfalls, and they saw valleys. The way we would currently explore such a place in space exploration is we would take a picture every 10 feet, and then we would send back all those images. That's not a very efficient way of describing what it's looked like. Well, actually, Lewis and Clark didn't even have cameras. They had to make drawings, and they basically drew a map, and they said there's some planes here, and they made some drawings of the planes. When we go to some place like Titan, when we go to another star system, we want to look at the data and figure out where there's some clouds, there's some limb, there's some rivers, there's some forest, and say, draw a map of the forest and the clouds and things like that, and say, this is where we saw those, and send back some exemplars. So this is a much more efficient way of communicating what the world, the alien world we go to looks like. So that's what we need to be able to do. Also, the AI technology has the ability to go from data to knowledge, and that's what we're trying to automate. So this is actually commercial imagery where we use the texture cam system to teach it how to distinguish between the plume, the shadow, and the land. This is from the Eyjafjallajökull eruption in 2010. A lot of you might remember this because basically for 2 months it was very hard to fly between North America and Europe. And so we can actually train, again, texture cam here with random decision forest to recognize the difference between these, and then apply geometric knowledge. We know where the spacecraft is, we know where the sun is, we know where the mountains are, and then we can infer how high the plume is. To the scientists we work with, this is like magic. We've taken a stupid camera and we've turned it into a volcanic strength of activity detector, because the plume height tells you how vigorously the volcano is erupting. So this is now done all over the place automatically, and this is a radical new data set for the scientists to use. So I talked a lot about data-intensive AI. Since a large number of us are here for the ICAPS conference, what about model-based AI, like Rao was talking about? Well, this is an example of something where we're putting the computer's power to use at something very tedious. This is actually a 1-week schedule for the EO1 spacecraft, and these are all the things that we're making the spacecraft do. It's taking pictures, it's downlinking data, we're uplinking data, it's doing some maneuvers, it's pointing all the time, and the spacecraft has a model of everything that's going on for every single one of these activities. And it's not worth it for the people to have to take control of this and to track all of this. So what does the spacecraft know about? What does the AI know about? Well, it knows when I tell it to take an image or to calibrate. Really, I'm telling it to do all these lower level things, and I can rearrange them how I want. It's knowing that when I want to take an observation of Delft when I fly over, I have to be within certain range. I have to turn the spacecraft. I know it takes so long to turn the spacecraft. And it has to know much more obscure things. Before we implemented the AI system, the humans said, well, if we take these observations at a certain spacing, the instrument won't overheat. Well, in our planning system, we actually track the turning on and off of the instrument, and we track the temperature with a temperature model that we empirically derived. And the temperature model actually tracks the temperature of the instrument at multiple places. And the instrument is very finicky. It has to be just warm enough where you get bad data. If it gets too hot, you're damaging the instrument, and everybody hates you. It turns out that when we have this model, we can cram 33% more images into the schedule. And the scientists, of course, love that. They always just want more data. So this is an example of how the model-based AI is helping us to operate the spacecraft. The other thing that's quite remarkable about what the AI is providing is that now people who know nothing about the spacecraft can try and command the spacecraft. Instead of having trained aerospace engineers, I know it's dangerous to say this at TU Delft, which is a university that's very famous for its aerospace curriculum, we are democratizing space. Literally, for EO1, we had over 100 institutions around the world that had the right to submit tasking requests for EO1. There was even a smartphone app. So at JPL, we built the system with a web page that you could command from. It took a contractor to build an iOS and an Android app that you could task the spacecraft from. So that's the difference in the work division. Unfortunately, EO1, the mission ended in 2017 because we ran out of fuel. But don't feel sorry for us because we have a lot of other great stuff up our sleeves. For example, On the rovers right now, the Mars Exploration Rover and the MSL Curiosity Rover, there's an autonomous targeting system that lets the rover pick its own targets given high-level guidance by the scientists. The most high-profile application for this is, in fact, the laser on MSL, CAM-CAM. It's a laser-induced breakdown spectrometer. So we literally have a nuclear-powered rover on Mars firing a laser on its own. So when you talk about worrying about AI, think about that. Well, maybe think about that if you're with Elon Musk and you want to go to Mars. Like Rao said, if you're happy keeping the rover on Mars and the people on Earth, I think you're pretty safe. So what the laser does is, when you see all these images of Mars, they're all red. Why is that? Because there's dust everywhere, and the dust has a high iron content. But with the ChemCam laser-induced breakdown spectrometer, it fires this laser, it burns off the dust, it actually burns off the weathering of the rock, and we study what comes out there, and again, this is actually saying the spectra, so we can figure out what's inside the rock. And so, what is the AI doing, and how is it helping? Well, previous to the system, which is called Aegis, they would take a bunch of images at the end of the day, they would download those images to the ground, the humans would pore over these images, figure out where the good targets are, agree on them, and then figure out all these commands that tell you how to point the instrument to take the right images, okay, or to fire the laser. Now, that's all done by software. So the scientists say, here's some criteria for targets, and the image processing on board pulls out the targets, extracts the features, scores them, and then prioritizes them. So they can say, lays all the targets that are above some threshold and score. They can say, only, take the highest scoring target, or take all the scoring targets that are, over some size. And then, very importantly, the software can not only select the target, but then it actually figures out the right coordinates for taking the LIBS instruments, the images, and some of these are very complex, like image a line across this vein, or do a raster, a 2x2 matrix, or a 3x3 matrix. And the most important thing that happens here is the software also makes sure that the laser is not shooting the rover, because it's a very bad day if the rover shoots itself with the laser. Again, people are not very happy if we were to do that. And that's on MSL. There's a rover that we're sending to Mars in 2020 called M2020. It has yet to be named. I'm sure it's going to be named in a contest where children are going to be asked to vote, just like Spirit and Opportunity and Curiosity. And this rover is going to have an enhanced version of Aegis that has even more sophisticated targeting capability that allows it to look at the images and understand this is conglomerate, this is mudstone, this is a vein, and search for complex features like boundaries between different surfaces and target those automatically. Another way that this automated targeting is a great improvement is on Mars, the atmosphere is much less dense than the Earth. What does that mean? That means that the temperature cycles much more from day to night. When they did this manual targeting, they take the images at the end of the day, then overnight the rover cools, and then it heats back up, and you might even take the image at a different time of day, so the rover is a different temperature. That cooling and heating leads to inaccuracies in the targeting. When you take the image, you want to shoot the laser immediately before the rover has a chance to distort. But since I'm talking about M2020, and many of you are here for a planning and scheduling conference, and also, by the way, I'm a planning and scheduling researcher, of course I want to talk about planning and scheduling on board the Mars 2020 rover. So right now, the MSL rover is commanded from the ground, and they develop a plan on the ground, and then they uplink that plan to the rover. And pretty much it's very detailed, and the rover doesn't have a lot of flexibility. But that's not good, because those of you who know about robotics know that things never happen how you plan. And so that's in fact exactly why we want the scheduler on board the Mars 2020 rover. This is a simulation of a plan, and in this case we finished the drive early, and what we want to do on board the rover is adjust the rest of the plan. And in this case we just adjust it by bringing these activities forward. But maybe we had a 2x2 raster scan, and since we have additional time, we'll make it a 4x4 raster scan, or we'll do some additional science. So that's in fact what we want to do. And we're not just talking about that, this is actually our prototype scheduler that's actually scheduling these different activities, and it knows how to make sure that the rover is correctly heated up. It knows how to have the rover turn on and off in sleep to save energy, and put all these activities in. And so this will enable the rover to be more productive because it can make these decisions on board. And planning and scheduling is everywhere. We supported the European Space Agency's landmark Rosetta orbiter mission. This is actually the complex observation campaigns from MTP-9, so this was right around August of 2014. And we also did the data management automated scheduling for the orbiter as well. So these are basically all the different data buffers. The instrument data is streaming into them. You have to figure out when to downlink the data, when the antennas are available. It's basically a several hundred variable decision problem that could be decided in near real time, so that if the scientists make some proposal to observe, the data, to observe the comet, we actually could support, the operations team could support it and say, well, we can't do that because we can't get the data down. We can do that because we can get the data down. And then other people might not know that, in fact, NASA has a network of antennas all around the world that can communicate with spacecraft all around the Earth. So they're in California, near Madrid, Spain, and Canberra, Australia, and they're located that way because they cover all directions as the Earth rotates. So these support approximately 80 missions, and we have to schedule all of these and allocate these antennas to track the different spacecraft to get the data down. There's actually 3 different systems. One that looks out 5 to 10 years out and says, if we launch that mission, can we actually support it? And the worst place to launch a mission is near Mars, but not actually at Mars. They have this wonderful technique at Mars. They just point an antenna, and then all of the spacecraft can communicate with the same antenna. But if you're near Mars, then nobody wants to service you because you can't use the Mars antenna, and then you're competing with Mars. So we schedule all of these using an AI system, and the AI system knows about all the different ways to satisfy the services or the kinds of support that the mission needs. In fact, recently we introduced what's called link complexity-based scheduling. It used to be we had operators that build up the communications links and tear them down and control the equipment. The problem is that it's very expensive to have these people build and tear down these different equipment links all the time, even though they can do it in automated and in software. So it turns out it really requires the operator attention at the start and the end. And so since we have a model of the operator attention needed, we actually can schedule the requests so that they don't align those different things. And for a very important mission, we can even put margin in. And so this allowed us to go from less than one link per operator to over 3 links per operator. So this is a great multiplier on the productivity of the overall system. So you don't actually even have to go to space to find applications of AI to space science. This is great work by Kiri Wagstaff, where they do automated analysis and correlation of targets and different science topics. They analyze thousands of papers from the Lunar and Planetary Science Lunar Planetary and Science Conference, so that they have now what's called the Mars Target Encyclopedia. So you can say topics like hematite. Hematite is very interesting to scientists because it's a substance that forms in the presence of water. So scientists can say hematite, and basically they now get all these green dots are targets that are correlated with hematite. They're discussing targets, areas on Mars where hematite was discussed. So think of this as a super duper version of Google Scholar that knows about spatial and contextual significance here, and scientists are using this every day now as we speak. Machine learning is used to deal with the vast amounts of data that come down. This is data from what's called the Intermediate Palomar Transient Factory. Every night this generates 10 to the third hits. A hit could be like a supernova or an undiscovered asteroid. In theory, it could be an undiscovered planet. That's just not very likely. And so the astronomers applied all of their best image processing, statistics, and so on, and they still had 10 to the third of these hits per night. we added as a subsequent phase to this a random decision forest classifier that continuously does quality control and sort of searches for particular kind of problems with bias. And now they get the 50 most likely hits, plus they also take a random sampling to measure the bias. And so the scientists are looking at the best, most likely interesting science events, not a random sampling, before they took a random sampling of 50 of the 10 to the third. This problem exists in an even worse situation in radio astronomy because the amount of data they have is much larger. There's a project called the Fast Transients Experiment, VFaster, using the Very Long Baseline Array. You might have seen about a year ago there were a bunch of stories in the news that said we found an alien civilization because these particular radio signals are indicative that there's some advanced civilization in this particular star system. While I can't say that that is not the case, I don't really believe that's the most plausible explanation. However, these fast radio bursts have been happening for decades, and the scientists don't really have an explanation for them. So we have a triage system that triages down from 10 to the 5th of these hits for 24 hours to the most interesting ones that the scientists have found. And again, there's continuous quality control and retraining. So this enables the scientists to focus on the most relevant data. Getting a little closer to home, climate change and our evolving Earth is kind of a very important thing for all of us. People are applying machine learning, actually this is the one deep learning slide I'm going to have here, to what's called detecting fugitive methane emissions. So using the conventional technologies, a match filter, they were actually able to determine a certain quantity of methane that's emitted by what are called fugitive methane sources. These are like factories or like a fracking well or a leaky pipeline. They're actually able to drive that down almost 2 orders of magnitude by adding a follow-on deep learning trained system. And this is very high-profile work. The seminal papers from the Proceedings of the National Academy of Sciences. This is very important for enforcing IPCC. And a lot of people didn't think that you could actually detect these point source emitters of methane. That's now been proven that you can do that, and AI is a key part of that. So I'm now just going to touch on a few more out there topics. We've had rovers all over the surface of Mars. We want to put them underneath and explore caves. Caves require much more autonomy. You can't communicate with the rovers while they're in there. And by the way, the rovers die all the time. So they're all going to die eventually, but we want them to go as far in and explore as far as possible before they die. So we're working on different coordination protocols that actually trade off trying to coordinate versus giving up on the neighboring rovers, and in fact seeing how far we can get in, and this is showing them applying different coordination algorithms to explore deeper into the cave. This rover is kind of dead now, but the rovers are going on. Eventually all of them die, and the last rovers are just trying to go all the way in on their own, which it kind of is sad, and they fail. Which is, by the way, the same thing that happened to the Sojourner rover way back in 1997. The base station died, the rover was fine, so it kept driving around trying to communicate back to the base station, and it couldn't, until Watney got there in the movie. So other things that we'd like to do. Since I'm here in the Netherlands, you know, the home of S-Tech, I have to talk a little bit more about Rosetta. It's a fantastic mission, but we had to plan it out 4 to 8 weeks in advance. So when we had narrow field of view instruments like the microwave instrument that tells us what gas is coming off the comet, we did these broad sweeps across the nucleus, several kilometers wide. But what the scientists actually want to do is they want to track the plumes and measure across that. So we were able to convince them for the next mission, who knows when that will be. This is a collaboration with Holger Sirks. We can actually use active contours and different machine vision processing techniques to track these plumes. And as an added side bonus, the poor graduate students don't have to label thousands of these plumes in hundreds of images as well. So now I'm going to touch at the very end about how we can find life and other planets and beyond our solar system, and how AI is a critical part of how we're going to go and do that. So Europa is of interest to a lot of scientists. We have the Europa Clipper mission. We hope to have the Europa Lander mission. But I'd like to go one level beyond that. Why do we care about Europa? Well, when I was a kid growing up in the 1970s, sorry, I'm admitting how old I am here, Scientists thought that life could only exist with photosynthesis. You need sunlight, you got to have the plants and so on, or maybe algae. The beautiful thing about science is it can be wrong and it can correct itself. In the 70s, they found hydrothermal vents on the bottom of the ocean, and life existed there in the absence of sunlight on the gradients, in particular nutrients and chemicals in the water, the chemosynthesis. And so there's now actually, if you Google LUCA, least universal common ancestor, there's a theory that life began there in the absence of photosynthesis, not in the conventional theory, which is you have pools of amino acids and lightning hits it in the shallow water. I'm not saying that's the primary theory, but now that's somewhat credible. So we want to go to Europa and other ocean worlds like Enceladus and search for this life. There's a little bit of a problem. In order to have this mission, we have to fly to Jupiter, then we have to go to Europa. That's going to take years. We have to land on Europa. That's pretty hard. Humanity is, I think, less than 50-50 at even landing on Mars. The terrain is worse on Europa. Then there's this little problem that we have to melt through the ice cap, which is tens of kilometers thick. Luckily, I'm an AI person, so that's somebody else's problem. So let's worry about what happens when we get through that ice cap. We have to go hunt for hydrothermal vents. We have to search for life. We have different instruments that will tell us things. We don't actually think that we'll go up to things like this, because first of all, that would be a very dangerous thing to do. But we do know that, yes, there will be a NASA logo on our submarine. And if you think this is all science fiction, one of the members of the AI group was actually on an icebreaker about a year and a half ago, courtesy of Antje Botius, who is the expedition leader at the Alfred Wegener Institute in Germany, in Bremerhaven. They were about 100 kilometers from the North Pole investigating the only known hydrothermal vent site, or believed hydrothermal vent site, in an Arctic environment underneath ice. And what Andrew's job was to study how they searched for the hydrothermal vents, how the human experts searched that, and to study how we might develop an algorithm to do that on its own. Why does it have to be on its own? Because when the submersible is underneath the ice cap, it can't communicate back to the Earth except when it's at its base station. It might have a 1 to 2 year mission. It will have to go months on its own without interacting with humans. So it has to be autonomous. And so, in fact, the different techniques that we have are to do spiral searches coming back and to then do nested searches so it looks for the signal. Unfortunately, the screen's too dark, but you can't see. This is a simulation with an actual tracer where we simulate a plume and we search for the plume. When we run across it, we actually follow it back to its source. So we hope that we can develop these algorithms so that someday we can find this life under ice. And of course, Enceladus is another place that has been observed to have plumes. This is a concept developed by Masahiro Ono at JPL, where we would land and then we would send these climbing cliff bots that are actually tethered, and they have to climb down the crevasse all autonomously. And the reason why it's autonomous is it's very hard to communicate back intermittently. These individual things have to sort of go out. You have a lot of them because you know you're going to lose a bunch. They actually have to screw themselves into the ice for all of you robotics people, because when the plume comes out, it's much more than the force of gravity. So we need to be able to autonomously explore this area, get the data, and come back. And then, just if that's not hard enough for you, burrowing through the ice, let's imagine we go to another star. The nearest star, Proxima Centauri, is about 4.5 light years away. With the current conventional technologies that we have, no wormholes, no warp drive, you have solar sails, you have RAM fusion drive, you have nuclear propulsion. It's going to take, optimistically, 60 years to get there. If you want to go to the TRAPPIST system, which is tens of light years away, it's going to take you much longer. When you get there, you can't command that spacecraft. When you send it a command, it'll get it 4.5 years later, and it'll tell you back, I got that command 9 years later. So the spacecraft has to go there, look at the planets, figure out which one to get into orbit around, how to get into orbit, what's it going to map, what's it going to image, what does life look like? These, to me, are the ultimate challenges of artificial intelligence and the search for life. So That to me is a great challenge to all of you in this room, maybe your children, maybe your children's children, to build the AI capable of going to another star system and finding life so we can make contact and know whether or not we're alone. So I just want to leave you with a few take-home messages here. AI is being used all over the place in space. I hope that you've seen that from my talk. But the flip side of that is these are a tiny, tiny fraction of the number of places where I believe that it can be used. And furthermore, to me, space exploration is about understanding the universe, about understanding if we're alone in this universe. And AI is critical for that problem. We need AI. We cannot solve that problem without AI. There's a lot of great, further details for people who are interested in finding out more about these things that I just touched really quickly. Of course, I want to acknowledge this talk. I work at JPL, and then leave you with the JPL mantra, which is do dare mighty things. You'll be surprised what you'll accomplish. Thank you very much.
Thank you, Steve, for a very inspiring talk. Let's use a few more minutes of all our time to, for a few questions. I see already one here.
So what came to my mind is with the increased automation in space exploration systems, do you see actually a need for human exploration in that area? Because if we improve our AI systems that much, that why do we have to send humans there? It's just dangerous system. Our robots can do any job we can do, probably better.
No, I wouldn't say that. Let me answer that question in two parts. So I think we need to send human places, but for the meantime, it's much easier to send robots there. And I don't think the robots are doing as well as the humans. They do these experiments where they have human geologists go out into the Mojave Desert and they go and conduct a field campaign. And then they have experiments where they have rovers and they have people in a trailer operating the rovers like they would do if it's on Mars. And it's much less productive. But to send it, if you think it's bad sending a submersible underneath the ice of Europa, try thinking about how you're going to send a human there. So I think in the meantime, we need to send robots there, and certainly you have to send robots before you send humans there. And then even when you have humans there, you need to have the AI so that the humans aren't doing mundane things. So a huge amount of time on the space station is in what's called inventorying. That's basically getting the crap from the ground and putting it someplace and then going and getting it when you need it. So that's a great thing that we want to automate. We don't want to have the humans doing things like that. So I would say we want to use the AI to get there before we can send humans there. And then even when we send humans there, AI is essential so that the astronauts can focus on the important things, not the mundane. And then I'll take this chance to poke at Raoul a little bit. I agree completely with what he said. We want AI to be able to interact with humans. But on the other hand, I don't think we want to wait until all AI can interact with humans. Because how many years were we all using keyboards and basically the humans had to adjust to the computer and we were sitting at these horrible CRTs? If we decided in the interim during that time period we were not going to use computers, it would be a very sad world. So clearly the end game is to be able to interact with the computer and the AI in a way that is good for humans. But in the interim, we should do the best we can. Other questions? There has to be some kind of Delft prize, right? With the prize for that?
Chocolates inside. This question is to both Professor Rao and Steve. How do you define AI? It's not like before this term was coined up, we didn't have smart and intelligent algorithms. We always have been looking at data, coming up with, analyzing it, coming up with nice formulas and everything. How do you define it?
I try not to define it because it's a moving target. So there was a time when, in order to get in an elevator, there was a human involved. There was a time when to connect two people by phone, there was a human involved. There was a time when you booked your airplane flights, you talked to a human. Now people would say, why would you do that? And do we think that's really intelligent? Well, maybe not running the elevator, but maybe booking the airplane flights, maybe the routing algorithms when we all use Google Maps to get someplace. It's a moving target, and I'm sure that 10 years from now, people will be doing something that, like, I will think is crazy, you know, because I'm older, right? Yeah.
Okay.
Final question?
Other? Yeah. I'll also mention if we have people that are, you know, not so bold and wanting to ask the question in public, I'm sure you can accost Rao and I later on and hunt us down. Go ahead.
Yeah, hi. So I want to know how good are the cameras on your satellites? So could you, I mean, in theory, track what people would do on the street or something, like do some crazy surveillance? I don't know. I mean, this is some kind of, I'm a very neurotic person, so.
I would say I'm not qualified to answer that question. But they can already see quite amazing things. There's just also pure physics involved. As you get closer, it's much easier. So personally, if you're worried about people spying on you, I wouldn't worry about the satellites. I would worry about the quadcopters that you're seeing all over the place, because they can use a much cheaper camera to launch a satellite into space. You know, even the cheapest one is going to cost millions of dollars. You know, the expensive ones might be billions of dollars. But anybody can go down and, you know, for $500 buy one of these drones and fly it over you. And again, it's just the physics, you know. It's 1 over d squared, right, for the resolution. Other?
So, and are you using, maybe you could use this really
I don't think you're going to get an answer out of me.